Okay, good morning everyone. Uh, I cannot open my mouth really wide because I just had surgery. Surgery in my dental removed. So it's a little bit swollen. So my plan today, maybe we are going to finish early. Okay, I need to go had another plan at before 9. So maybe 9:45 or 9:50 or 8:50 we are going to finish. Okay. So actually we are going to have a new sections today, new chapter, the multiple integrals. Okay. I will start with just a little bit review. The integral that in calculus 1, if you remember, this is start by, so if we define the integral from a to b of some function f, this is, we can rewrite as a limit as a sum of the the rectangles. Okay, so we can approximate using the rectangles that slice the curve. Okay, if you see the area under the curve, we can approximate with this rectangle, and we can plus all the area, and that is our approximation for the curve. And by the limit, if we cut the rectangle, like maybe first is 8, and then we increase 80, 100, 1000, then the rectangle will be becoming more smooth, and it will performing under the curve really the approximation really going to closer to the real value. And so we can see that we need to define this integral with using limit. So we can imagine that if we slice a lot of rectangles, this will can be calculated, and it will be closer to the real value, or in the limit, then this is the exact value of our integral. Okay, that's the calculus 1, right? Calculus 1. So we look at the important thing here is the area, right? Area under the curve or the function. Okay. Now, since in calculus 2 we deal with the multivariable, which we have f x y, at least we have f x y. So we are expecting that this will be related to volume, okay, to the volume. So we are going to see it in 3 dimension, okay, in 3 dimension. So if we start to look at for example, this surface here. Oh, sorry. So if we look at the surface here, let's define the f x y as z. So the height, we can control the height. And if we project the surface to the xy plane, this r, and this r we can project here. Maybe put it beside. So if we project here, and then with the same approach as we did in calculus 1, we slice this rectangle. We slice and then slice in x and y direction, so that we can have this small square, and small square. Okay. So the r here is, we can define in terms of the area. So area from A to B multiply with the area from C to D. Okay, that's the R. Okay. And this can be defined also in terms of that it's supposed to be in XY, and it's in the 2-dimension elements on real numbers.
in which that the A is actually the same thing, but this is more complete notations. And that's R. And then the S, and then let S be a solid above the R, okay?
Which means that this one here that has this shape in the 3 dimension, and that's the S thing.
Okay. Above R and below F, XY. So S we can define in terms of X, Y, Z, which this is going to be element in 3 dimension, as we can see that we start from 0 for the height in Z-axis until Fxy, and the xy is the component of the real number. So our goal now is to find what is the volume of S. Okay. Okay. And to approach finding this volume, if the calculus 1 we slice the area, now we are going to slice this. So imagine like a cake. You cut the cake. You cut the cake and cut, and you see that this is how we cut from the top. We cut and make a small square. So we are going to have this slice, and of course that the surface, if we cut like the using the and imagine that there is a rectangle here, we are going to have this kind of like, we still have like a not really smooth right, in the top. And then you could imagine that for obvious reasons, like similar with calculus 1, when the rectangle is like more and more, this becomes smooth, right? So this is just to show you that if n is maybe not really that much, how many the rectangular volume, it will be like having rough this the surface. But if we have more, then we are going to have a smooth. Now we are going to approach this, that this volume, okay, so volume of the box is basically the height, which is multiplied with the delta A. Delta A is this area, and this is the height. So we multiply that with the delta A. That will be our volume of one box. Volume of one box. And now, since we have many boxes, then we are going to add all the boxes. So the volume, then volume, or maybe let me write volume of S approximately we can write volume, or maybe write with approximation like that, is this double sigma of, let me write here, I equal 1 until m, and j from 1 until n. I and j is to get the x and y, because we now have two, right? Before in calculus 1 we only have x, So we have only one sigma. And then we write f xij and then delta a. Okay. Okay. Now, of course, then if we add more m slices and n slices, then you can imagine that if this is going to be higher and higher, maybe closer to an infinite number, like maybe really high, and then we can take the limit as n approaching infinity for this m and n, then we could see that this volume can be written as the integration, or the sigma become double integral. Okay, it's become double integral. Okay, so let me write in the next page. So this is going to be the definition of the double integral. So if we have double integral of f over the rectangle R, then we can write double integral with R. R need to be defined x and y, like how much the x and y value, like from which point to which point. Okay. And then we set up the dA as this delta A, and we can set up like dx dy or dy dx, and then this should be correlated with the dA. For example, if we have dx dy, then the inside will be the x and the outside will be y. Okay. I will show you in the later part. And this will be, so the f is, we call integrable. We can integrate if limit exists, which means limit from the definition. Okay, if the limit definition exists, then we can say that f can be integrated. Okay. And I think we can agree that all continuous functions, by default, they are all can be integrated. And this part, the sum part. So if we take only sum, I forgot to write this. Let me write again. So if we just compute only the approximation, this is we call the volume, or yeah, this is called the double Riemann sum. Okay. If you remember that in calculus 1 we have the Riemann sum, which only one integrations and then only one sigma. Now we have double sigma. And I don't think this is necessary for now. We can check like what is the example on double Riemann sum. But it's actually, we compute like one by one. For example, we slice like maybe only having like this. If we have the R like this, so suppose that this is the R. Let's say this is R11, R21, R12, R22. And we know the point here, which means we are going to calculate the area. That will be the delta A. And then later
if we know the function, then we are going to put all x, y here from this part, and then we calculate the area. For example, okay, let me just show you. Here is this is 2, 1, 0, 1, 2. This is y, x. So this is the r. The function suppose let. So this is example. Let z is 16 minus x squared minus 2y squared. Okay, so this is an elliptic paraboloid, and we divide the r become 4 rectangles. So m equal n equal 2. So it become each one of them 2. Okay. So r is here is 0, 2, and 0, 2. Okay. And each of the area, so delta A, will be only 1, right? The square of each r. So the volume, taking the sigma, I will write this is going to be F 1, 1 delta A, okay, plus F 1, 2 delta A, plus F 2, 1 delta A, plus F 2, 2 delta A. Since all delta A is 1, so we can focus on the F. Okay, so F11 we put 1 into the equation. So 16, 15 minus 2 is 13, and we put the other one as well. So basically we've I think I will put the point here. So 1, 1 is here. Oh, 1, 2 is here. 2, 1 is here. 2, 2 is here. Okay. So this will be for the right and top point. But actually, you can try with different point. For example, 0, 0, 1, or 0, 1, and then 1, 1, and then 1, 0 in this one. You can also check. As long as all these 4 components, they have all intersection. For example, this blue point, so R12 has this, R11 here, 21 here, R22 here. But you can try different point as long as you can include all the square. For example, 0, 0, 0, 1, 1, 0, and then 1, 1. This also can be implemented. Right? Also here also can be implemented. This also can be implemented. So you can choose with any point as long as each one represents 1. So each point represents 1 rectangle. So you can just plus all the volume. Volume will be 13 plus 7 plus 10 plus 4, 34. And remember that this is the approximation. So V is 34. Approximate by double Riemann. Okay, so this is just approximation. We are not really going to discuss much about approximation, but this is how we solve the integrations through the geometric shape of the rectangle and the square. Okay, so from the boxes we find each volume and then plus all the components.
And we can also use this definition of the double integral as directly a volume that is in between the rectangle R and below the surface Z. So we can also write this. This is basically the same thing, but we can write the definition as this. So if the function R a positive function, means it's above the xy plane, okay? So not in below. So if it is it's in between of the xy plane, and then it is below the surface, that we can have the solid, that we can define the solid volume as double integration on the rectangle on the xy plane as fxy dA. Okay, this is just another definition. Basically the same thing. Okay, so what you need to remember is we are going to look at the volume in between the rectangle and the surface itself. Okay. So this is always be the case for our assumption. So we assume that the function is always positive, means that at least if this is the xy plane, so it will be above this gradient plane. Okay, so we can compute the volume here. So as long as we know the function and we can project it into this xy plane, and we can write the volume as this. Okay. So for example, this is the surface, so we can project them here, or we can project like small things and make it the small boxes like that. Okay. Okay, now we move to what we call as the iterated integrals. Okay, this is, I think, the last part for today. So iterated integral. So to get into this double integral, suppose that we have a, b, c, d, and then this is f, xy, dx, dy. So we start all the integration from this inside integration. So this is the first step. Okay. So for example, if you have x squared y, and then this is dy dx, what we need to do first is we can try from the inside, okay? Which means we are going to focus on dy. So we integrate only y, and x is like a constant. So we integrate that. So this will be half x squared y squared. We plug in 1 and 2, and we still need to write the outside. Okay. Well, sometimes if you are in the maybe working on some problems, maybe you can just compute this first somewhere else, and then after finish you can put here the result when you have finished all the computation, and then integral one more. Integral one more. Okay. So we can see that if we put 2 and 1, we are going to 4 minus 1, so we will be having 3. So this will be 3 over 2 x squared dx from 0 to 3, and this will be, we can integrate x squared become 1 over 3 x cubed. So this will be half x cubed from 0 to 3. And of course, we can just plug in. Since 0 we can ignore, so we focus on the x equal 3, which is result 27/2. Now, the interesting thing on this computations is, since this rectangle, if we remember that before, we always say that this dy dx in terms of dA, we can set up like dA can be dy dx or dx dy, as long as these two are constant. So let's say we can just flip the integration. So let me write again the integrations, but we flip 1, 2, 0, 3 x squared y, and then this is going to be dx dy. Okay. Now what's happened is, now we are going to start from x. Okay. We start from x, which give you 1/3 x cubed y, and then we put 0, 3, and still we need to write the outside integral, which is 1 to 2 dy. And this will be equal to, we put in 3, become 27/3 of y dy. And now we integrate with respect to y, then we get 27/3 half y squared, and then put 1 and 2. Now 1 and 2, if we plug it into y squared, this will be 4 minus 1 is 3. So 3 cancel here, so it become also the same 27/2. Okay. So both has the same result. Okay. This indicating that we can flip out this two integrals as we want. Okay. Sometimes maybe if you look the functions, maybe if we just integrate, maybe difficult. But if we flip, maybe it will be more easier. Okay. So sometimes this will be helpful. Okay. Sometimes this will be helpful. So how we can flip out is actually, if this is a constant, it's not a problem. We can flip out anytime. You can flip the integration. You can start with dx, or you can start with dy. It's up to you. And you can flip up as many as you want. Okay? That's what we call the Fubini theorem. Okay? The Fubini theorem. So Fubini theorem is f is continuous, of course, and the rectangle should be in a constant, which means a, b are constant, c, d also constant, okay? X and y. Then you can flip out like these two x and y. We can start from any variable we want. And by this theorem, if we visually look at the graph, it's actually the same thing. We want to find volume here, so we can start from this area here or area there. Will be the same result. And also, aside from the Fubini theorem, another theorem that is quite helpful are if we can separate the functions completely. For example, we can see that the x and y is actually we can see that they are not really in one system. So for example, this part here, our function. So let me write here that if we write x squared y, let's say we are writing this. Actually, we can write, since this 1 to r dy, we can write separately 1 to y dy, and then the dx will be this. Okay, we can also do this. So this will be a half y squared,
from 1 to 2. And this will be 1 over 3 x cubed from 0 to 3. So this will be 4 minus 1 is 3, so 3 over 2 multiplied with 27 over 3, which is 27 over 2. The same results, okay? So you can flip, right, compute inside the integral and then outside the integral. Or you can separate x and y, and then working y, working x, get the same result. So any method is going to be the same result. This is what we call the iterated integral. So you can start the iteration from any like you can start from x, you can start from y. Okay. Okay, I think I will just stop until here because I need to go somewhere else. So tomorrow, hopefully, I can get to your makeup. Do you think it's difficult to make up? Okay, right? Okay. I haven't seen the whole score. It's still in your TA. But I think it's okay. So if not tomorrow, maybe Friday I will give to you. Okay. And next week, not this week, next week, Thursday, we will have a quiz on chapter 14. Chapter 14. Okay. And hopefully this Friday I can review, or maybe next Wednesday I can review chapter 14. Okay?
You said Thursday, right?
Next week, Thursday. Yeah, not this week. So not tomorrow. Okay.